Hi everyone, so the goal of this video is to understand gravity. The learning targets are to explain gravity in normal force, compare and contrast mass versus weight, and execute calculations for normal force and the force of gravity. Alright, let's do a quick check to see if any of you have any misconceptions. Now, some of these statements might be true, they might be false, I'm not going to tell you right now. But I want you to maybe pause the video and think about what you would say for each statement. So first of all, true or false, heavier objects fall faster than lighter objects. The second one, true or false, there is no gravity in space. And the third one, true or false, mass and weight are different things. All right. So, like I said, I'm not going to tell you the answers to those right away. I might have you try to work through those misconceptions if you have any misconceptions. I'm not saying any of those things are true or false. You have to figure that out. So gravity. Gravity is a mutual attraction between all things that have mass. Now, believe it or not, different things that we see in our everyday life have some gravitational force between them and they're attracted to each other. We don't really see that for smaller objects, even objects that are the size of us or buildings or things like that. For us to really see the force of gravity, we have to be looking at much bigger things. So we might talk about planets and stars and other big objects in our universe. Those are examples where you'll see the force of gravity attracting things towards each other. So one example, as you can see in the picture here, is the moon. The moon has a gravitational force and the Earth has a gravitational force, and they're attracted to each other. And so that kind of leads to the moon orbiting around the Earth. Now, gravity pulls objects down towards Earth. When we think about our Earth and our everyday life, right, gravity is what pulls things down. I think everyone in high school kind of knows that already. But we're going to be looking at a more mathematical thing, and we're going to be looking at different forces and a few additional ideas that might challenge your thinking. And then we will be using some mathematical equations to talk about the force of gravity. And so the acceleration of gravity is negative 9.8 meters per second squared. So a couple things to point out about that number. It's negative because it's downwards. So far we've only been talking about left being negative and right being positive. But think about up and down motions. That happens all the time in our everyday life. And just like in math class, when you look at a graph, we're going to treat up as positive and down as negative. So the gravity would be a negative number, and it's an acceleration. So the units are meters per second squared. All right, so in physics, mass and weight are not the same thing. Mass is measured in kilograms, so that kg there stands for kilograms. But weight is measured in newtons. So we might have this equation here where we might say Fg equals m times g. So let's explain what those variables mean. So Fg, like this, the F stands for a force, and then the little letter here tells us what type of force we're talking about. In this case, we're talking about the force of gravity. Well, we need an m and we need an a for a force. We need mass times acceleration. Well, we have a mass, and then g is just a special type of acceleration. It's the acceleration from gravity, and it's always going to be negative 9.8 meters per second squared. Anytime we're talking about an object on the surface of Earth, this is the acceleration that we're going to want to use. So let's look at a quick example. So what is the weight of an object, a 10 kilogram object? Well, we don't know the force, right? Because we're asked for the weight. But we know the mass, and we know the acceleration is negative 9.8. So, I mean, I'll do the math real quick, but for some of you might already kind of have an idea of what we're going to do. We're going to do a force is mass times acceleration. Except in this case, the acceleration that we have is the acceleration from gravity, which is g. So we're just going to take our 10 for our mass, because our mass is 10 kilograms, and our g is negative 9.8. We're going to multiply those two things. So 10 times negative 9.8 is going to be negative 98. And the units that we use for force, as you might remember from previous lessons, is newtons. So we write a capital N to represent our force. So just to be clear and to show what our final answer is here, that would be our final answer. Okay. All right. And so here's a really good model that you can use, and that might help you think about the difference between mass and weight. Your mass does not change no matter where you are in the universe. So let's take this little guy here. Maybe he's 80 kilograms. He'd be 80 kilograms on Earth. He'd be 80 kilograms on the moon. He'd be 80 kilograms in the middle of space. He'd be 80 kilograms on Jupiter. But his weight would be different. He weighs a lot more on Earth than he does on the moon. And you might see videos of astronauts kind of taking like these huge jumps and these huge bounds as they go on the surface of the moon. And that's because they are actually lighter on the moon. They weigh less on the moon. Their weight is less. Their mass is the same, but their weight is less because the force of gravity on the moon is less. All right, so why don't things fall towards the center of the Earth? If we're talking about gravity and gravity is just like pulling things down towards Earth, then why don't things just fall towards the middle of Earth? There must be something stopping it. There must be some equal and opposite force, and we call that the normal force. So the normal force is the force that a surface exerts on objects. So you're talking about like a surface, it could be the floor, it could be a table, it could be anything like that. Or like even in this diagram here, whatever this surface is resisting the force of gravity. So gravity or weight is pulling this down, and then you have normal force kind of pushing up. It's equal and opposite to gravity. All right, so do a quick example. What is the force of gravity and the normal force of a 1 kilogram textbook on a desk? So we can kind of already have a model here. We can see our textbook here. I mean, I might want to draw a few things. I might want to draw that there's a force of gravity going down, and there might be a normal force going up. All right, and so those two should be equal and opposite. All right, well, the force of gravity, I know my mass is 1. That's easy. My gravity is negative 9.8, negative 9.8. And so the force of gravity is, well, I'll put a question mark for now. That's kind of easy. You can see that the force of gravity is mass times gravity. And so we have 1 times negative 9.8. All right, so we have 1 times negative 9.8. That becomes just negative 9.8 newtons. All right, that's the force of gravity on this on the textbook. And so if that's the force of gravity, then I kind of already know the normal force. Ready? It's the same thing, it's just equal and opposite. So if this textbook is not accelerating, which it's not, it's just sitting there, then the normal force, and I'll put an N to represent the normal force, the normal force is just positive 9.8 newtons. So again, these numbers are equal and opposite. They're both the same magnitude, but one is negative and one is positive. And if I was looking at the net force of this, well, the net force would be 0. This plus this would be 0. And that means that the textbook would not be accelerating. And that's obvious because it's just sitting there on the table. Okay, I hope that's obvious to you, and I hope that makes sense. All right, here's a harder one, though. You're like, why do I need to know this? Well, here's one that's kind of related to a real-life engineering problem. So you're building a small bridge across a small river. The bridge can sustain 1,500 newtons of force without breaking, but any force greater could cause the bridge to break. Can a 170 kilogram person cross the bridge? So I think what we should do here is we should write out what we know. We kind of already have a model here. We can think about a person walking on this bridge, and there's going to be their force of gravity, and then the bridge is kind of resisting their force of gravity. But we want to know if this force is too big for this bridge. All right, so we know that the mass is 170. And the key to this problem is to remembering that the force of gravity comes down to the acceleration of gravity and mass. So we need to remember that the acceleration from gravity, it's a negative sign, negative 9.8. All right, and now we need to figure out what is the force of gravity on this person. All right, and if it's greater than this number, 1,500, then this person can't cross the bridge. We got to figure something else out. All right, so force of gravity is equal to m times g. This number is 170. 170 times negative 9.8. All right. And so that equals, bring up my calculator. It's always hard to multiply numbers that have decimals. Can't do that very easily off the top of my head. 170 times 9.8 is 1,666. All right, that's too much. This person has too much mass. That's a negative number, right? So this number is greater than this number. That means this person cannot cross the bridge. They have to find some other way to get across. Hopefully this person can, hopefully they're carrying like a big book bag that maybe they can give to somebody else and kind of get their number down, but that's going to be kind of tricky. So this is an example where, this happens a lot in any kind of engineering project where you have some kind of material or some kind of building that can withstand a certain force, and then you want to think about, okay, how much force are we allowed to put on this object considering the material it's made out of? It's a common civil engineering problem when you look at cement versus metal versus whatever substance you're using, whatever material you're using. You want to think about how much force can this thing withstand and how much can we actually put on this thing without it collapsing or actually making sure that the structure is sound. So some real world applications to why we want to know the force of gravity. All right, maybe one more thing here that I want to talk about. I'll just quickly go over this idea of the force of gravity. So the force of gravity, you might have seen this equation before, but the force of gravity for big objects, we might use this equation where we have the mass of one object times the mass of the second object times this gravitational constant, all that divided by the distance squared. So if we have two planets, or maybe a planet and a moon, the force of gravity between those things comes down to the mass of those two objects and how far apart they are. This equation is called like the universal gravitational equation. That's because it's true anywhere in the universe. It's true on the surface of Earth. It's true for planets far away. But it's especially useful when we're talking about really big objects that are far away, like planets and stars and things like that. All right, so I just want to point that out. It's an equation that you might see, if you ever take a college level physics, you might have to play around with this equation. So I want you to be familiar with it. All right, you might have some practice problems to do after this, so good luck with that.